Okay, we should get started. So, hi everyone, welcome to the special seminar that we're having today at a weird time. But we're still having a lot of people here, and because we're very excited to welcome our visitor for today, Professor Dan Green, who's an associate professor at the University of California, San Diego. And Dan Green does not want me to tell you any more of his CV, but he is a very excellent cosmologist, and he's going to tell us some really cool stuff about neutrinos and cosmology. So take it away.
Awesome. Thanks for the introduction, and thanks for the invitation to be here. I was once a faculty member here, and I'm going to talk about work that I'm doing in part with Joel Myers, who is a former citizen as well, who I got to know when he was a postdoc here. And we've continued working on neutrinos together, in part with some collaborators as well on this first paper with Nathaniel Craig and Surjit Rajendran. And hopefully this title will make sense to you as we go along. So my plan for talk is I'm going to introduce the subject of cosmic neutrinos and why they're interesting, at least in part to me. Then we're going to get into neutrino mass and how it's measured in cosmology. We'll talk about some funny things going on in the data that suggest negative neutrino mass and some possible implications for beyond standard model physics. Okay, so when we think about the history of the universe and what happened at various epochs, we can't separate it from what's going on with the laws of nature. So nature decides how things interact, which in turn is related to what the universe does and how it responds to the stuff in it. So one way to see that is that when we start changing the laws, so we create new ideas to solve various cosmological problems in particle physics, we see that the different aspects of this picture may change. So you may create a model to explain some phenomena of nature, and it introduces a phase transition, it introduces new particles, it changes the energy or time scale of the universe. And these are things that we want to test by looking at maps of the universe. So these maps are also shaped by the laws, and by getting into the maps and understanding how they are shaped by the individual particles that make up the universe, we can learn what the fundamental laws are and at the same time learn more about the history. Okay, so a canonical example of this is dark matter or dark sectors. We know this is in the data. We know this is in the universe from cosmological data, but the exact microphysics of dark matter and dark sectors is encoded in here. I'm just focusing on the cosmic microwave background. And you can see that over many decades of mass, different effects show up in the CMB in different ways. So dark matter annihilation for certain mass range shows up in some aspect of the CMB. New light particles shows up elsewhere. Different interactions between dark matter and other components of the universe show up in different observables. So through one map, it's like doing many different experiments that has many different controls over what the microphysics is doing. This should be compared to the experimental landscape for dark sectors, which again similarly covers many decades of mass, but in this case it has to be covered by a bunch of individual experiments that just cover pieces of this large mass range. So cosmology is particularly compelling in part because it gives us such a wide range of physics through a single map. Now, it's not just that it gives access to a large range of physics, it's actually very competitive with the lab. So one way you can tell your experimental friends how much better cosmology is to say, we've already detected dark matter via cosmology at 120 sigma. And as I'll explain in this talk, we've detected the cosmic neutrino background at 30 sigma, and neither one of these things has been ever experimentally verified in the lab. What is the origin of this superiority of cosmic maps? One is the very high temperatures or very high number densities that are relevant to the early universe. So when you have a lot of stuff, even very weak effects can become important. And then the second thing is that after they're produced, typically new particles are produced because of these high temperatures and number densities. What we're left looking for are gravitational signals, and gravitational signals have the advantage that they are not easily hidden. So when you're looking for the direct collision of, say, dark matter with a standard model particle, if the dark matter does not couple to the standard model in the way you like, you can't see the effect even if it's there. Whereas if you're just looking for the gravitational effect of dark matter, you can't screen it away. And so we go back to this plot, you'll notice a huge fraction of these things we're just looking for the gravitational signal. And so we're able to see these different effects very robustly to changes to the model and how it actually talks to the standard model. Okay, so the purpose of my talk is I'm going to illustrate all of these things in the context of the cosmic neutrino background. The cosmic neutrino background on this plot is a relic from about a second after the Big Bang. So cosmic neutrinos at very high temperatures were in thermal equilibrium with the standard model. They're a weak process, so just by dimensional analysis, the production rate of neutrinos goes like G Fermi squared, the weak coupling constant. And just to make up units, that means that the production rate goes like temperature to the fifth. So that means at high temperatures, it's very efficient. But at low temperatures, T to the fifth drops off much faster than the expansion rate of the universe. And so at some temperature, they're no longer produced efficiently, and they just dilute from expansion. And again, by dimensional analysis, you come up with a temperature of about 1 MeV for when this occurs. Now, the important thing about 1 MeV is that it is higher temperature than the associated mass of electrons. So what happens is that the neutrinos decouple. They're no longer in thermal equilibrium at a temperature before the temperature drops below the mass of the electron. When the temperature drops below the mass of the electron, you get Boltzmann suppression of the electrons, which means the entropy that used to be stored in E plus E minus pairs gets turned into entropy of photons, which means you heat up the photons, but the neutrinos aren't around to be heated up, they're now decoupled, and so you find that neutrino temperature relative to the photon temperature is dropped by this famous factor of 11/4. So the ratio of those temperatures cubed is 11/4. Now this is often converted into a number which we call N effective, which is the effective number of neutrino species. It's literally just the relativistic energy density in neutrinos, so like a T to the fourth of neutrinos, multiplied by a bunch of stuff so that that number would be 3 in the limit that my calculation that gave me 11/4 is exactly correct. So it's just meant to spit out the number 3, but it's just a measurement of energy density. Now, because that 11/4 is not exactly correct, it gets about a 1.5% correction from the fact that there's still some production rate of neutrinos and the fact that the plasma is not actually just a dilute gas. You get a slightly higher number. That's not to say there are fractional numbers of neutrinos in the universe. It's just that these constants were not quite right to make this exactly 3. Again, it's just a measurement of energy density. And so this is just a parameter that tells you if the energy density of neutrinos is about what you expected from the standard model. Now, I should say this error bar here is a theoretical error bar from the calculation of the energy density of neutrinos from Big Bang nucleosynthesis. Okay, so the best way that we have to get a handle on an effective and the number of neutrinos in the universe is through the cosmic microwave background. As I'm sure you've all heard many times, the cosmic microwave background is the relic radiation from 380,000 years after the Big Bang, when the universe became neutral and photons no longer scattered off of electrons, but just came free streaming towards us. Now, prior to this time, so right before the atoms become neutral, or hydrogen becomes neutral, you have these photons scattering off of electrons that are then talking to protons just via electrostatics. And so together, they form some relativistic fluid that's all tightly coupled together. So this thing is floating around, you have this relativistic fluid. The neutrinos, again, they decoupled at 1 second after the Big Bang, so 380,000 years later, they're only talking to the rest of the universe through gravity. And same with dark matter, just standing on its own, talking to this through gravity. And so when we zoom in on the CMB and we look at what these temperature fluctuations are, they're just sound waves of this original fluid. So when you see when you see a snapshot of the CMB, you're just looking at the density fluctuations of a relativistic fluid, so they're propagating sound waves through the universe 380,000 years after the Big Bang. Now, when we look at the power spectrum of fluctuations in the CMB, you've probably also all seen this plot before, and you've seen this acoustic spectrum. Now, what this spectrum is we take every spherical harmonic on the sky, and then we average over all the different spherical harmonics that have the same angular scale. And the fact that they add coherently tells us that all the sound waves at that time were in phase. So when we take sound waves that were moving with the same wavelength but in different directions, they all had to be of the same phase, so that when we add them together, they look like a cosine. So again, this would be a solution to the wave equation for these sound waves, but if they all came with random phases, when we averaged over them, we would just get some smooth shape. But the fact that we see the acoustic peaks means it's a pure cosine, which if you're used to solving differential equations is kind of surprising, because usually you have both a sine and a cosine component as a solution to the wave equation. And so the absence of this sign is telling us something important, which is that this was not caused by mixing up a fluid at the time of recombination, but instead this in some prior phase was needed. So we actually produced these long before recombination. The expansion of the universe drove this term to zero, and we're left with this pure cosine, which arises because of the physics of inflation. But the fact that it's not there, we have a good reason for, and it tells us something about the history of the universe. So in particular, we don't have a sign. We have an amplitude, which we think comes from inflation. It's some random process that generates the statistics for this amplitude. And then we have this cosine, which is totally deterministic, and it encodes all the physics that's going on at that time, 380,000 years after the Big Bang. So for example, the ratio of baryons to photons is determined by the speed of propagation. And then there's corrections to this formula that include a variety of other effects that I'll talk about as we go along. Now, the fact that these things factorize, so the fact that there is inflation times this deterministic function, is part of the reason we are able to determine so many cosmological parameters simultaneously. The physics of inflation does not get confused with the physics of recombination, and so we're able to measure parameters related to both simultaneously, and thus we get these nice tables of very precise numbers from cosmology. Okay, so from that, we want to determine how many neutrinos there are in the universe. And so the way that we do that is by looking at this picture. What we're really looking at is, as we go to the right, we're looking at sound waves that propagated for longer and longer in the history of the universe. So remember, we have this cosine CSKT, so more time means more oscillations going to the right. And so as we look at this picture, we're seeing physics that was probing earlier and earlier times. And so as you go to the right, these modes experience more and more radiation, more and more of the universe that was dominated by radiation. Now, even though neutrinos are diluted compared to photons, they're not diluted by that much. And so during this era, they make up 41% of the total energy density of the universe, which is a big deal because it means any gravitational effect that changes the CMB on this part of the plot is getting 41% of its contribution from neutrinos. So that's not so bad. If we can go and measure effects that are 41%, that's not really so impossible to think about. So the main way that neutrinos are determined from the cosmic background is the way they change the expansion of the universe. So the expansion rate is determined by the energy densities and the stuff that makes up the universe. And so at that time, it's mostly radiation. So it's, again, 41% of the expansion rate is coming from neutrinos. Now, the way that that shows up in the power spectrum is to change the damping tail. So specifically, what's going on as we go to the right is that photons are diffusing out of their potential wells. So you have these potential wells made by baryons of dark matter, and the photons want to come out of them by a process that looks like a random walk. That random walk, like any good random walk, goes linearly in time, or the distance squared goes linearly in time, or the distance goes like the square root of time. But the only time scale in the problem is the expansion rate, and so by changing the expansion rate, you change how much time there is for this diffusion to operate, and thus you see this big effect on the tail. That is basically how this number is determined from data, and so just from the CMB alone, we measure an effective is 3 plus or minus 0.17, which is quite a strong measurement that's consistent with our standard predictions. Knowing that this goes like t to the fourth, this basically means we're predicting the temperature very accurately for both the number and the temperature of neutrinos. You can also use this, so typically, I won't go into detail, but people who are interested in effective will also show plots like this that show how this constrains the possibility of more degrees of freedom in the universe. And so with this kind of measurement, you're at the point where you can probe individual additional degrees of freedom. So one extra particle would be detectable depending on the details of how toxic the state. Okay, now that is not that's not entirely the goal of my talk today. So what I'm going to focus on is what else we know about neutrinos from the CMB and other data sets. So one of the other things we know about neutrinos is they move fast. So neutrinos are quite light, so they move basically at the speed of light at 380,000 years after the Big Bang. And so what happens is that around that time, you have three components of the universe traveling at different speeds. You have this relativistic sound wave that travels close to the speed of light, but actually 1/√3 compared to the speed of light. You have these neutrinos that aren't banging off of anything, so they just travel in straight lines basically at the speed of light. And then you have dark matter, which doesn't do anything because it's super boring and it just sits and doesn't go anywhere. So the way to think about what's going on with these different components is to think the same way we drop a rock in a pond and we watch the ripples move out. That tells us about how the dynamics of the surface of the water are responding to fluctuations. So we can think of doing the same thing in the universe. We drop a rock into the universe and all the components, so we splash the dark matter, the neutrinos, and this photon baryon fluid all at the same time, and then we watch the spheres of evolution as they move outwards. Now, the dark matter, again, is boring. It doesn't do anything, so you put a spike in it and it sits still. It does not propagate outwards. The photon baryon fluid has this nice sound wave property. It does move outwards at the speed of sound. And in particular, because of the sound, the nature of the speed of sound in the system, nothing travels ahead of this sound wave. So there's a distance beyond which the sound has no influence. But the neutrinos traveling at the speed of light travel ahead of the sound wave, so they look like a supersonic effect during this time. And in particular, the presence of the neutrinos, their gravity creates perturbations through gravity creates a perturbation in the photon baryon fluid that regenerates the sign that would have been missing otherwise. So this sign can also be thought of as changing the phase of the cosine. And if you just added an arbitrary system coupled to the photon baryon fluid and you varied the speed of sound, you would see directly you only generate this phase when you're traveling faster than the speed of these sound waves. So this supersonic effect, the fact that you have fluctuations traveling faster than the speed of sound, directly translates into this phase. And that's a thing that you can go and look for in the data. So specifically, you can remove the effect of this change to the damping tail. There's an extra change to the overall amplitude, and you're left with this seemingly small change to the phase that just changes the locations of the acoustic peaks by a constant amount. And you can put that in as a template, which was what was done on the left, and it was to search for the effect of cosmic neutrinos. Again, you get an answer consistent with 3 relativistic neutrino species at about 5 sigma. But that's just for temperature. You can do something similar in terms of temperature and polarization and get it up to 10 sigma. So at 10 sigma, again, we're consistent with 3 relativistic neutrino species that travel at the speed of light. They don't bang into stuff. They are not sound waves. They are really free streaming particles. Now you can go further. You can look at the distribution of galaxies. Galaxies also inherit this acoustic structure. After the pressure from the photons is gone, the baryons just sit still, but they keep this ringing pattern. And this ringing pattern also has that same phase shift. So this is the BAO. This is the bump associated with the sound horizon at recombination. You see this pattern as we increase N effective, we move power from small scales to large scales. Again, consistent with moving stuff from being slower than the speed of sound to faster than the speed of sound. But when you Fourier transform that, again, you see this pattern of moving the acoustic peaks by a constant amount. And you can use that to exclude no cosmic neutrinos just from where all the galaxies are in the universe at 99.5% confidence. Okay, so the point of all of that was to establish how well we know the cosmic neutrino background exists and behaves like we think it should. Okay, that is going to be very relevant when we see funny things happening later in the talk. So, just from the CMB, we detect the cosmic neutrino background at 20 sigma. If we add in more data from Big Bang nucleosynthesis, we can get that number to 30 sigma. We see this phase shift in the CMB associated with traveling at the speed of light for these neutrinos at 10 sigma, and we've seen a similar phase shift in the distribution of galaxies at 3 sigma. This phase shift, because it has this origin in supersonic travel, is very difficult to fake by some other cosmic parameters. It's a unique signal of the neutrinos, and it's also because it has to do with causality on these enormous scales, it's very difficult to fake with nonlinear physics or other things that might be happening around that time. Okay, so just to summarize what we knew, let's say this is all about 2019, very, very strong evidence for the cosmic neutrino background that's consistent with all of our expectations. Okay, I'm going to pause here. Are questions about and effective what we know about the early universe of neutrinos? Everyone's happy or bored or both? Okay, massive neutrinos. Okay, so we know neutrinos have mass, so that is one additional complication in the story. So this was done in part in Canada through SNO, this fantastic measurement. But it doesn't determine the absolute mass scale of neutrinos, it just determines that there's a difference of mass between different flavor eigenstates. So what we know is that there are 3 different masses, and we know some splittings between those masses determined from neutrino oscillations, but what we don't know is the ordering of those masses or the overall mass scale. So in cosmology, we're instead only sensitive to the sum of the absolute values of the individual masses. Roughly speaking, once the temperature of the neutrinos has cooled down so that they're non-relativistic, the total energy in neutrinos just becomes the number density. This is just an expression for the number of neutrinos times the mass in each one. So they just become massive particles, so the total contribution of the energy of the universe is the mass times the number density. And so we just add up the total masses of each of those particles, and that's the total amount of energy in non-relativistic neutrinos. There are 2 scenarios that people discuss for neutrinos. There's the normal hierarchy, which is where one of the neutrino eigenstates is much heavier than the other 2. And because of the known splittings, that gives a lower bound to this number, the sum of neutrino masses of 58 millieV, or 0.058 electron volts. And then for the inverted hierarchy, where 2 of them are heavy and very close together, and one much lighter, you get a lower bound of 100 millieV. So these are lower bounds that we know from neutrino oscillation experiments. So these 2 numbers have set targets for cosmology. So your goal is you say, I know there's a non-zero number I'm aiming for, and ultimately what I want to do is try to measure a number that I'd be able to measure numbers that are this small at high significance. Okay, so what do we know already? So we've already established that we know that neutrinos are relativistic at 380,000 years after the Big Bang. And so that puts some kind of limit that the mass can be much higher than the temperature at that time. The temperature around recombination is sort of a fraction of an electron volt. And so when you take the data you have, you get something that's sort of like a quarter of an electron volt upper limit from current data. Now that's very strong, much better than all the lab-based experiments, but still farther than these numbers that we want to hit. So to do that, we need to actually add data that's not from the CMB, but from some lower redshift where the neutrinos are actually non-relativistic. Okay, so the challenge is that neutrinos are actually still a very small fraction of the matter in the universe. So once they become non-relativistic, I add them to the cold dark matter and the baryons to make up all of the matter in the universe. And the fraction of this matter that's made up of neutrinos is like 0.4% if I'm at this lower bound of 58 millieV. Now, if you were just to sort of guess what the size of a signal of neutrinos would then scale like, you would typically expect it goes something like this fraction of a percent times some order 1 number. So a lot of proposals for signals of neutrino mass end up having this problem that you have to do a sub% measurement in order to have a hope of detecting a number this small. And that's challenging because there's not that many parameters in cosmology that are known to less than 1%. The tool that seems very powerful for getting past this problem is to use the fact that neutrinos change how structure grows in the universe. So these are two simulations that correspond to a universe with only massless neutrinos and one with massive neutrinos. And what you're supposed to see here is that on the right, this is the universe, without massive neutrinos that has deeper wells. So what happens is that neutrinos, massive neutrinos, which are on the left, are suppressing the formation of structure. So the idea here is that even though the neutrinos are matter, they're still quite hot. So even at redshift 0, one of these neutrinos at 58 millieV will be traveling at something like 1% of the speed of light, which is generally too fast to fall into the gravitational wells made by the dark matter. So roughly speaking, you have this component of matter, but it doesn't want to fall into wells, so it doesn't help the universe cluster. So the way that one can understand this is that there's these two fluids in the universe. There's the dark matter and the baryons, which are kind of cold things that are moving around slowly. And then there's the neutrinos, which are also a kind of cold fluid, but they're moving around at some non-zero speed. And that means that neutrinos have an effective gene scale, a scale below which they don't want to cluster. Now, you can take these fairly straightforward equations, you can plug them in a computer if you want, or you can even solve them analytically, and you'll find two properties of the solutions to these equations on small scales. The first of which is that there's no density contrast in the neutrinos. So the neutrinos just don't want to cluster, so they are just uniform on small scales. That's the kind of obvious consequence of the first picture. The less obvious consequence of the picture is that it changes the speed at which the dark matter clusters. So even though the dark matter is still able to grow, it's not directly talking to neutrinos, the neutrinos are speeding up the expansion of the universe without contributing to the gravitational wells. And so as a result, the gravitational wells grow more slowly by this factor here. So this is the growth rate of the dark matter baryon gravitational wells. And so the first effect just shifts the amount of power in fluctuations by just removing the neutrinos. So this first term here just says, less of the matter in the universe is clustering than you think. But the second term is an integrated effect that acts over the whole history of the universe. So once the neutrinos are non-relativistic, dark matter stops growing as fast as it wants to, and as a result, there's an integrated effect that goes like the log of the redshift where neutrinos become non-relativistic to the time we observe this effect that builds up the influence of the neutrinos to be a much larger number. And so instead of being a fraction of a percent, you get this sort of order of few to sometimes even 10% effect from cosmic neutrinos. So here you see this sort of this effective gene scale, which tells you that that it's only on small scales that the neutrinos don't cluster. But this amplitude is something like almost a factor of 10 times the fraction of energy in neutrinos. So it's a much bigger effect suppressing the structure than it would be if it was just an order 1 number times the fraction of neutrinos. So it turns a fraction of a percent effect into a several percent effect, which makes it possible to look for the mass. Now, there's many things that probe structure, and many of them have been proposed as ways to look for the suppression of structure. The one we're going to look at today is CMB lensing. CMB lensing has one obvious advantage, which is that this dashed dotted line here is roughly the nonlinear scale. You'll notice that CMB lensing mostly has its signal to the left of this, meaning it is in a nice and linear regime. Whereas typically galaxy clusters, cluster counts, etc., live in the nonlinear regime and therefore are harder to control over the nonlinear effects that might affect the signal. The slight trade-off is that you'll also notice the CMB lensing signal goes to much higher redshift, and so the signal is slightly smaller because we have that ratio of logs of redshifts, where higher redshift means that we slightly reduce the size of the signal. So what we're looking for, though, is we're going to take the lensing of the CMB from all the intervening matter. We know how to do that and reconstruct maps of all of the lensing along the line of sight. And from that, we're going to try to extract how big this number is compared to expectations. Roughly speaking, this is the signal one is looking for, this few percent suppression of the lensing amplitude. This is much smaller than the error bars we can observe, but it looks just like an overall constant. We can't resolve the shape of this. The shape is all lost in error bars. So all we get is the overall amplitude. That is actually what makes measuring neutrino mass hard, is that you have to measure, that the overall amplitude is indeed controlled by the fraction of energy in neutrinos, but it's also controlled by many other things. So for one, it's controlled by the amount of matter in the universe. If there was no matter, there would be no lensing. So the overall signal depends on how much matter there is to lens the CMB. It also depends on the primordial fluctuation of amplitudes, the primordial amplitude of fluctuations. If there are no fluctuations in the universe, there'd be no lensing, and therefore the signal also has to go away if you turn off the fluctuations. And so what you're actually measuring is the product of three numbers you don't know, and one of them is the one you care about, the fraction of neutrinos. So you need to measure these other two numbers very well. So the first thing we need to do is determine with high accuracy the amount of matter in the universe. And the other thing we need to know is to know the primordial amplitude with sufficient accuracy to determine this number. Now at this point, I'm going to pause and comment on the slide. The ordering I made this slide several years ago, and I have not changed it on purpose, because when I made this slide, I included this comment that I thought this was the easiest, this was the second easiest, and this was the hardest number to determine. So this was decreasing order, or increasing order difficulty as we go down. And so again, I'm telling you that now because this is not biased by having seen what will now happen when we talk about current data. Are there questions on the status so far? Now everyone's happy, or bored, or both. Yes, I see some nods, which is at least better than sleeping. Although I don't mind if anyone sleeps. I'll need a rest. All right, so that was supposed to be the story. The story was that this DESI, so we can do some, we could piece out the history of what was going to happen. We needed to measure these three numbers. Planck had measured the first number, Planck had measured the third number. We were waiting on DESI to come and measure the second number. DESI, again, made this plot was made long before DESI had data. This is what DESI is supposed to do. DESI is going to come in, it's going to have really tight error bars on the amount of matter in the universe, and it was going to come in and say, the normal hierarchy, not the inverted hierarchy, it's several sigma, detect neutrino mass, everyone is going to celebrate, and it was going to be fantastic. And then DESI released its first data, and it looks like this. Okay, so the green curve is the measurement. There's a question in the content.
Yeah. Are you able to place more stringent bounds on the individual material?
So, okay, so the answer to that is that as we go down, because of the known, so if we assume the splittings, then as we go down, we eventually reach the point where we know one of them is effectively massless, and we pin down the other two. The problem is that we're going to run into problems where we don't know anything. However, if one of the species was very heavy and had nothing to do with the splitting, we would see that as some feature in the data. So we know that all the species are light-ish and consistent. We believed were consistent with the experimental bounds on the split. Okay, but so now here we are today. The green curve is what DESI's 1-year data, BAO data combined with Planck told us. Oh, Planck plus ACT, sorry. The key thing here is that it's excluded the inverted hierarchy at 3 sigma. Okay, so the upper limit was something like a 95% confidence. DESI's number is like 70 millieV. It rules out 100 millieV at 3 sigma, and so it did what it promised. It was going to exclude the inverted hierarchy. we've got the normal hierarchy, hooray, that's what we expected. The problem is that it's almost excluding 58 millieV as well, and so that's better than expected in terms of excluding models of neutrinos. Now, this was not actually, it was news to me. This was exciting to me because I had internalized this story that we were waiting for DESI to tell us what was going on. But actually, there are already hints of trouble with EBOS. EBOS had done this analysis where they similarly had this sort of pretty good constraints, and they fit their data to a Gaussian, and they noticed that their Gaussian fits were all peaked at negative values of the mass. Now, the error bars are wide enough that that seemed like maybe just a peculiarity of the data. Again, they were consistent with both the inverted and normal hierarchy, but the bound is actually quite a bit better than forecast because the central values have all shifted to negative values. So this is suggestive, right? You look at this plot, you see the likelihood for the neutrino mass is still going up when you hit 0, which strongly suggests that if I were to continue mass to negative values, I would find that the central value is some large and negative number. And so that's what we did. We just took this signal, which is this lensing signal, and we said, okay, what we're looking for is a suppression of structure proportional to the neutrino mass. We can just take that suppression of structure and turn it into an enhancement of structure with the same exact shape proportional to mass in the same way. So we just take that template and we just shift it so that we allow it to be both negative and positive by just reflecting around the 0. We don't touch the energy density here, and the reason is that we didn't want to put like a negative energy density into any of these Boltzmann codes because we thought that would cause problems, whereas just changing the profile of the lensing amplitude is easy to do and doesn't propagate anywhere. Okay, so here is what those signals look like. So this, again, this was the 58 millieV, this is 100 millieV, and this is minus 160 millieV neutrino mass, just to give you a sense of what this looks like in the fractional change to the lensing amplitude. I didn't choose minus 160 by accident. That is our best fit value, more or less. So this is the green curve is what we get from analyzing the CMB plus DESI data, now allowing neutrino mass to be negative. Now we exclude all of the physical neutrino mass at 2 sigma, and it actually excludes 58 millieV at 99% confidence. Okay, so this is what the data looks like. Okay, it's definitely not what we were planning for. Okay, so what could be going wrong? Okay, again, although I will talk about BSM physics, I tend to not believe that anything is BSM physics until every possible alternative is exhausted. So let's go through all the possible explanations, which are still probably the most likely things that are causing the problem. So as I said, we're going to work backwards. The worst thing, the thing that ahead of time I would have told you is the least trustworthy is the measurement of the primordial amplitude. And the reason is because of the optical depth of reionization. So the problem is stars around redshift 6 or 7 start reionizing the universe, photons start scattering back off of those free electrons, and so they create kind of a frosted glass effect. So with frosted glass, you can't see the small scale details, but you still see like big shadows. So the same is true in the CMB. The reionization doesn't disturb the amplitude of structure on very, very large scales, but on small scales, it damps it up by this factor e to the minus 2 tau. So you literally need to know this number and not the product of AS times e to the minus 2 tau. So the problem of knowing the amplitude is the same as the problem of knowing the optical depth. And the problem is the history of measuring the optical depth is not great. I think people who were around for the first WMAP release are probably the most scarred by the history of the measurement of the optical depth. That's this data point here. Now, you can see this kind of strange, it's one of these strange patterns. The numbers have been consistently going down over the years. Some of these numbers don't look entirely consistent with previous error bars. But so we've gotten this number down to be pretty precise, but given the history, I think people are naturally skeptical of this measurement. What I've drawn here are 2 lines. The The dashed line here is what the optical depth would need to be consistent with 0 neutrino hits. So that doesn't look so bad. I can get back to 0. Seems within the regime. Now it's still, with these error bars, still about 2 sigma, but okay, believable. The problem is that if I want to get to 58 millieV, the number's up here, which is about 7 sigma. Okay, so I'm not going to get to a detection of neutrino mass without a totally wrong measurement of the optical depth. So if someone comes along and says, yes, the optical depth is actually up here, then we'll be able to detect neutrino mass, but many people would have had to make major errors. I think Peter would probably be one of them with this Planck data. So we should definitely trust these numbers, or at least definitely it's very suspicious it'll get that high. Okay, so although I didn't believe that this number was that robust, we're talking about robustness like of these numbers. These are 3 different Planck likelihoods, so you can see how hard it is to measure by the fact that these are still scattered, but probably unlikely that it's up here. Okay, and so one way to test, so this was just by eye. This is the history of the measurement, and those are some rough lines. You can add different Planck likelihoods, and you can see exactly this effect. So if I take, say, this point, and I do the analyses, it shifts by a little bit. So taking the likelihood that has slightly higher values of the optical depth indeed moves it back towards more positive masses, but you see by not enough that it's really going to totally change the picture. Okay, so next is the BAO. Particularly DESI has some funny looking points. These 2 points in particular are quite far from not just the best fit Planck, but also from previous data from BOSS. So you can try swapping these points out. So you can remove this point and replace it with the BOSS point, because let's say you don't like it. And it shifts the values a little bit, but again, not by very much. The reason you would think this would help, though, is that another way, again, the change to the lensing amplitude can also be accommodated by just changing the amount of matter in the universe. So you see, there's slightly different shapes, but not enough that you can really tell in the data. So you could get here by like what's this, 4.5% increase in the amount of matter in the universe. Now the problem is, again, you go back, so here it has a history that's a little bit more stable. This is the DESI point. It does look a little off from the previous point, so maybe it's supposed to be a little closer up here. This is still the number you need to get to if you want to explain 58 millieV. Again, something like 7 sigma. So on its own, omega matter is probably not going to solve the problem. Okay, maybe it's the lensing. So maybe Planck just made a serious error in their lensing analysis. And fortunately, SPT put out a paper last week which answers this question, so I don't have to guess anymore. So SPT made the same measurement of lensing, so they looked at the effect of CMB lensing on their data, and basically everyone consistently finds that the lensing amplitude is higher than expected. So varying amounts, but this is with the BAO data. This is the SPT lensing data alone. These are 3 different experiments with their own lensing data. This is the combined. All of them are consistently high. Actually, the SPT lensing uses only polarization or reconstructed a lens, which is totally different than how Planck does it. So it does seem consistently like all these experiments are getting something like a high lensing amplitude, and it's high both in 2-point and 4-point lensing. So all of it points to the sort of consistent pattern of a high lensing amplitude. Okay, so that's where we are. I have gone through the entire list of things that I'm worried about as possible explanations.
So before you go on to that, is there any worry about just that the structure gets erased because of baryonic effects, or is it at the
Oh, these are
scale is
super
too large
large
that
scales.
you can't
These
have
are super large scales. You can cut. I think I even have the plot way back here. I can show you. Let's see if I've got it. So here you can see that even if I keep cutting the data to get short distance completely out of it, I basically keep getting the same sensitivity. So if you're really worried about it, you just cut, but it's really not in the non-linear shape. Okay. But that's also why it's going to be hard to do another measurement, because let's say galaxy cluster counts gives you a totally different answer. Well, do you trust the galaxy cluster counts, which are more sensitive to nonlinear effects and baryons, than CV lensing? So again, I made the order for a reason. I thought the CV lensing was the most robust, the most checks that it was valid. So that's the biggest challenge. Okay, so I'm just going to do a few minutes lightning DSM explanations just to give you a flavor. You can ask me about them in detail later. So the problem we're facing is that there's basically not going to be a better measurement of any of these numbers for a long time. So if the problem is the optical depth, we're basically got to wait till LightBird, which launches in the next decade sometime if we're lucky. So we're just going to be stuck with whatever the current optical depth from Planck is for a long time. We've played the game of seeing if more DESI or Euclid data is going to help change the situation. And again, the only way it does is if the current DESI and BOS data are just completely wrong, and we somehow discover that with more data. And again, there's not a lot of evidence that the problem is the maps, but we are going to get some better lensing maps from Simon's observatory. But again, there's no evidence that that's the problem, but maybe it will change with higher quality maps. So in practice, it means that for the foreseeable future, we're almost certainly going to be consistent with 0 neutrino mass, and possibly even likely negative neutrino mass, even as we add more data. So one way to explore these ideas is to say, okay, I can't get better measurements of neutrino mass, but I can at least ask what else could cause these effects and go look for those effects. So if I see something consistent with 0, what would it take to get to 0? And is that allowed by the data? Is there some other experiment I could do that would tell me if that's what's going on? So to get to 0 neutrino mass, I just need to erase the signal of the suppression of structure. So that's something that's easy to do in the neutrino sector. I just need to get rid of neutrinos. That gets me back to this no neutrino signal. Negative neutrino mass is an enhancement of clustering. There's no particular reason enhancement of clustering has anything to do with neutrinos at all. This would point to new physics of some other kind. So I'm going to separate these two possibilities and talk to them one at a time. So just getting rid of neutrino masses, there's an easy way to do this is neutrino decay. So you just take the heaviest neutrino, have it decay to a lighter neutrino and some new light particle. Because you only need to do this on the timescales of billions of years, this decay rate it's not hard to construct a decay rate that's totally fine with all experimental probes and neutrinos. Again, you need a few billion year decay rate. You can engineer that with incredibly small couplings, and it's not in violation with any obvious constraints. So this is a range of parameters that's like 5 orders of magnitude, where you'd be totally consistent with other constraints and still have them decay to erase a signal. And interestingly, the upper limit here is actually a cosmological bound from our phase shift. So if it was too strongly coupled, the neutrinos at 380,000 years out from the Big Bang would form a fluid, and they wouldn't have a phase shift. So you see how powerful cosmology is in focusing on these neutrinos. It's really hard to constrain this kind of scenario any other way. So this is a totally legitimate possibility for explaining the signal. Okay, so here phi, the question in the chat I think is what is phi? Phi is just a new light particle. It's often called a myeron. It would be like so a particle that would do this is something that would be a Goldstone boson for creating the flavor structure of the neutrinos. But yeah, there's easy to engineer models that have this new light particle that's consistent with experimental bounds. Okay, another option is to cool the neutrinos. The problem is the neutrinos are too hot. There's an easy thing sitting around just waiting to cool the neutrinos, and that's the dark matter. It's like a giant heat sink. So you just take the energy in neutrinos, dump it into dark matter, and that would do the job. And so you can see from this plot, this is just the suppression of structure as a function of temperature. So if you cool the neutrinos by a factor of 100, you basically erase the signal.
So that would require an interaction between neutrinos.
Correct. So you need to add an interaction between the neutrinos and dark matter. Easiest way to do this is with right-handed neutrinos. This is more constrained, but still a viable option. The main thing that's hard about this model is you actually need to have inelastic scattering. You need to dump energy, not just exchange, bounce off of each other. So there's some details of how you engineer a model. This one's a little bit more contrived. The decay is just super easy. You don't have to do much modeling. Okay, so those are kind of the obvious things to do. There's many more. Our paper has lots of dumb or somewhat dumb ideas. Okay, but now let's just quickly talk about getting negative neutrino mass. So what we need to do is enhance the lensing signal. One obvious thing that comes to mind is to think about dark energy. Okay, so dark energy changes both how you measure the total matter in the universe. It also changes how structures grow. And Desi had these weird plots that suggested something funny going in dark energy. So you have this expression here for the growth of structure. So you just need the this growth function dA to be bigger than it was supposed to be in lambda CDM. And just by staring at this expression, you can convince yourself the only way to do that is to have Hubble be larger in the past. Roughly speaking, you need this factor here to be smaller in the past, so it makes the structure bigger. That violates the null energy condition. Hubble is only supposed to get smaller over time. It's not supposed to get bigger. So it's smaller in the past than it is now, then it has to grow, and that violates the null energy condition. And so the regions where you expect to see this enhanced structure are precisely the regions where you should be violating the null energy condition. Now, even that sounds, okay, maybe you don't care about the null energy condition. The second problem is that that's great for explaining structure at redshift 0, which is this plot here. So this is the change to the amplitude of fluctuations at redshift 0 for changing the equation of state of dark energy. The problem is that dark energy comes to dominate the universe at redshift of 0.3, whereas our lensing signal is like redshift 1 to 10. So dark energy doesn't do much work on the lensing signal. It does a great job on the power spectrum redshift 0, but this is the same change now put on the lensing plot. So you see almost no effect on lensing compared to our neutrino mass signal, where at redshift 0 can do the job of explaining neutrino mass. So altogether, this is why dark energy is not a great strategy. Typically, when you analyze the data with variable equation of state for dark energy, you just get wider error bars, but you don't actually shift the maximum likelihood. And then if you impose that it actually obeys the null energy condition, it actually shifts to more negative values. So you get an even tighter constraint when you impose that you add dark energy with variable equation of state, but impose the null energy condition. So another strategy would be to change the 4-point function of temperature. So the way that this lensing measurement works, like the key thing that I really trust is this 4-point lensing measurement. So roughly speaking, the way that lensing works is that it correlates different temperature modes. So you see that if I have two temperature modes of different wavelength, that they get correlated by the lensing field. So if I want to reconstruct the power spectrum of lensing, the lensing reconstruction is what we 4 powers is equivalent to just measuring that correlation and putting it together, which is a temperature 4-point function. So you can just make a model for a 4-point function. So you have some primordial 4-point function that kind of looks like the lensing 4-point function, and that will shift the inferred amplitude. So here is a dumb model that you can make up where you just add an extra field that has a funny power spectrum, and that will make a 4-point function that kind of looks like the 4-point function. 4-point functions from Planck are very poorly constrained, so it's not so hard to hide this signal in the way they do analyses. So that's an idea for how you would generate an enhanced, the appearance of an enhanced lensing amplitude, but only via just increasing the 4-point function. Okay, so I'm going to summarize. I'm happy to answer questions or talk more about other things, but just to sum up, CMB plus BO shows some clear preference for negative neutrino mass. It's not limited to 2-point statistics. It shows up in this 4-point statistic, which is known to be more robust. It's hard to explain the signal by any one data set that you don't trust. And because of that, it's very likely to persist in the data for the foreseeable future. I'll be tested on that tonight because Desi has new papers coming out, and they have one on neutrino mass. So we'll find out if I'm right, but so prediction. It will look exactly the same tomorrow. Okay, so now that gives us an interesting opportunity to explore whether this could be due to something else that we're not looking for in the data right now. So there's lots of ideas, like I listed a few, but our paper has many, many more. ways in which you could generate this kind of signal without being in obvious conflict with other experiments. Just getting to 0 points to some kind of new physics in the neutrino sector. If you really want negative mass, it could be due to all kinds of things. I pointed to primordial non-Gaussian because that seems like the easiest one to evade. There's some long-range force ideas that make gravity stronger in the dark sector, or some other ideas. But there's a lot of room to come up with ideas that then hopefully we can test and will give us some better idea whether there's hope that this is, we can understand the signal by some new physics, or it's probably just a bunch of systematics we don't understand. Okay, I'll stop there. Thank you.
Neutrinos being heavier in the past help?
So would neutrinos being heavier in the past help? So the problem is that the structure is integrated over time, right? So the easier, the reverse would work. So another scenario would be like some environmental effect that turns neutrino mass on at late times. So that's, I would say the obvious way to get to zero mass would be the opposite, where you just you have them be effectively massless until redshift 1, and then you say, oh, there's some local, it's because of the matter density becomes big, and that causes some effect, so it inherits a mass through interactions. There was a literature on time-varying neutrino masses to explain the cosmological constant back in the early 2000s. I think Ann Nelson was on some of these papers, but they were hoping that time-varying neutrino masses would look cosmologically similar to a cosmological constant. I don't think that works very well, but you could take those models and basically just do this with them, just by changing some parameters around. So it's an idea. I don't think making them heavier in the past helps, because you want them to be massive today for the neutrino oscillation experiments, and you pay that price from the log somewhere. So you kind of want to turn that off. Other questions?
Just remind us why actual negative neutrino masses make no sense.
Why actual negative neutrino mass makes no sense. So you really have to have negative energy density associated with the neutrinos. So it's not that the sign of the neutrino in the Lagrangian, because I've basically already taken an absolute value of that sign. So I really mean that it's some null energy condition issue that I just don't, if I start putting negative energy running, it's like some ghost, and then I just have a.
You're actually taking the absolute value somewhere.
Yeah, so the absolute value was there in the expression when I wrote it, because my sum of neutrino masses really means the sum of the non-relativistic energy densities of each species. So I took that absolute value times the number density to give me the mass.
Can you explain in brief what goes into the ineffective calculations when you get this 1% deviation?
They put everything in, they put in neutrino oscillations, they put in, so roughly speaking, the way the calculation works, the key quantity is entropy. So what happens is basically you count, entropy is conserved in thermal equilibrium, so basically you can count the entropy of the universe before the electron-positrons annihilate. You count the entropy of the universe after there's no more electrons and positrons, and that gives you the 11th force. But the entropy of a system that's coupled, like QED, so there's actually just binding energies associated with QED, means that the entropy of the universe in that plasma is not the formula that just sums up all the free particles. So there's a correction that just comes from that, that's just entropies of, the entropy of QED at finite temperature. And then there's an effect that comes from the fact that when the electrons and positrons are annihilating the photons, they still produce some neutrinos. So the neutrinos are not in equilibrium, but they're still being produced at some finite rate. That error bar is so small that I know it gets effects from the, neutrino oscillations in there too, but it's way below the sensitivity we can measure. So I think those two things are good enough to get you about 1%-ish. And so now whether it's 1.5 or 1.25 or something, that matters a little bit. There's a question in the chat. Yeah, I guess I would say that, okay, so the question is negative neutrino mass like some signal of, so there's phlogiston, which suggests something going the wrong direction. I think the easiest interpretation is just to say it's an increase of lensing. So there's lots of ways to increase lensing. That's all we have evidence for. There's not evidence for the actual negative energy density associated with neutrinos. And actually all these analyses, like the analysis I showed from SPT never uses the word neutrino. It just says, what is the lensing amplitude compared to expectation? And they find that that's consistently high. So I think I would just start with there's lots of ways you would expect the lensing amplitude to be larger. That's probably an easier way to get into what's going on than to worry about neutrinos specifically.
So for the optical depth, Taurus is coming up. I can't remember the timeline though, or it's forecast.
Which one's Taurus? That's the balloon?
It's a balloon one,
Okay.
yeah.
It's the balloon,
But
okay.
I can't remember what the schedule is and what it's.
Yeah, so, I mean, Barth is not here to tell us about the challenges of ballooning, I guess, but so I would say I actually was on a competing proposal for measuring optical depth of the balloon. There's also CLASS, which is trying to measure it in the Atacama. I guess my answer would be and this would be my same answer for the other parameters as well. Like, okay, sorry for scrolling, everyone. Okay, let's go back to this plot. Okay, so if a balloon or CLASS, which has again never been proven to measure the optical depth, came with a number here, I still kind of believe plot, right? Like it's still all sky. I still have way more control over it. So if they disagreed by 7 sigma, now, okay, obviously my confirmation bias would say, oh, but I expected to get positive neutrino mass, so maybe it's right. But again, just scientifically, like I have more faith, like somewhere I have to explain why the first time I've ever used a new technique to measure that experiment deviates from this long and difficult history of trying to measure it from all sky CMB experiments. If they differ by 7 sigma, like why I trust the balloon
It's
over.
where you get the first black point, is so smack on the last W map point.
Well, it's all systematics, right? So, yeah. Or
Yeah, I mean,
all
but it's just really hard. And so again, that's where I come down to is the challenge, the real challenge is even if an experiment came along that differed by enough sigma to explain the signal, would you believe it, right? And the problem is I gave you the list that I believe the most, right? Same with if one of these cluster counts comes and says, no, we see the cluster count consistent with positive neutrino mass, you say, well, what's wrong? Like, I trust CMB lensing has fewer concerns. It's larger scales, away from nonlinearities, away from baryons. The way we do it has these sort of beautifully understood systematic techniques for eliminating systematics. Now SPT is doing with the E to B mixing, which is super clean. Like, a really nice way to measure something without worrying about foregrounds, et cetera. So everything points to these are the things I would trust the most. And so even if I came along with a new measurement that went in the direction I wanted from a particle physics point of view, if you didn't tell me the answer, if you didn't tell me the sign, you just said it differs by 7 sigma, which one's right, you would I would have already trusted these ones more. Yes?
So the title was "No News is Good News." What's the good news?
Well, you should remember that 2 of the authors of the papers are particle phenomenologists. So the good news is that it can be a signal of new physics, right? So if you're, again, the best explanation as a pessimist is that it's all 3 of these things are wrong by 2 sigma. So no one of them is wrong enough that it makes you lose sleep, but they all went in the same direction by just enough that collectively they're wrong. But if you don't, other than that, this model is super easy, right? It's totally consistent with everything. It gets you back to being, within a sigma of where the best fit is. The true answer is probably larger lensing amplitude than the minus 160. It's probably consistent with 0. You get down to 0 pretty easily without disrupting any of the rest of physics. So that's the exciting part, is that there are built-in, totally unconstrained ways to get something that looks like what we're seeing. Realistically, I don't believe that, but I'm just, but that's the type. Does that make sense?
gonna ask you at this point, I mean, what's your comfort or discomfort level in accepting this as the solution?
So the thing that's nice about, okay, so my discomfort level, my discomfort level is, again, I don't like magical fairies that I can't see as explanations for things. So I'd be totally happy with this that I could go and see the signal. So there are cosmological signals of this, right? Because it does mean that as you go to higher redshift, there is some information here. It's just really hard to get at. Like, I think once you're in the regime where this is true, there's, it's hard to tell, but it doesn't let you go below 0. So again, you can in principle rule out this idea, but again, there's a lot of parameter space where you would just be like, I'll never know if this is the answer or not, and that's unsatisfying, right? So, but to be fair, this model was written down for reasons totally unrelated to cosmology at all. These couplings were actually written down by people who were trying to explain the structure of masses in the universe. So if you're just like, why does the universe organize itself into masses that are hierarchical in a certain way with certain mixings? There's a whole model building universe of people trying to do that, and you land on stuff that looks like that from just trying to explain the structure of masses. So it's not that you engineered this model post facto to explain this. This model was out there. The bounds on this model have been around forever. Papers were written on this, going back to the 90s. So it's not that you contrived a model to get this. So in that regard, I also feel better than the one where I create a model just to get away from to explain a signal that I don't see.
Complete naivety, with tau wants decay, with tau muons do not, and I'm sure there's a standard explanation for that, but I don't know it. You probably do.
Sorry, with
I mean that the heavy electrons do decay, but the heavy neutrinos don't. Is that an obvious?
Oh, so they actually do decay in the standard model. The rate is just so incredibly small.
Okay, so they do decay.
So they do decay. Just the standard model rate is way too slow to
I
do
see.
anything
Okay.
useful.
Yeah.
So this, you just need to increase it to be cosmologically well.
Enormous.
Okay, we're 10 past the hour, so we can continue discussion upstairs with the snacks. And yeah, let's take things.
Yeah, that's cool.